Have you ever used a translation app and just marveled at how it can take a short three-word phrase and turn it into a perfectly constructed seven-word sentence? It's not magic. It's actually a really clever design pattern called the encoder-decoder architecture. So, right there, that's the central puzzle, isn't it? Mapping an input of one length to an output of a totally different length. A simple word-for-word translation just falls apart. But here's the good news. By the end of this, you're going to understand the elegant two-step logic that makes all of this possible. And I promise, it's going to feel surprisingly intuitive. To really get a feel for how this works, let's just step away from the tech for a second. Instead, let's think about how a professional human translator does their job. The whole secret is right there in their process. So a good translator knows that context is everything. They don't just jump in and start swapping words. No way. The first thing they do is read the entire sentence from start to finish. They have to absorb the full idea, the complete intent, before they even think about writing a single word. Okay, so after they've read it, something interesting happens in their mind. They form a mental summary, a core thought. And what's really important here is that this thought is language independent. It's the pure meaning, totally separate from the grammar and vocabulary of the original language. This is the crucial middle step. And finally, with that one clear idea held in their mind, they start to generate the new sentence. Because they're working from the meaning, not the original words, the new sentence can be longer, shorter, or structured completely differently, but it still carries the exact same message. That's the breakthrough. Understand first, then generate. All right, now that we've got that human analogy down, let's map it directly onto the machine learning world. You'll see that the components line up almost perfectly with what we just talked about. First up, we have the encoder. This is a neural network, and its one and only job is to be the reader. It processes the entire input sequence, and its whole goal is to compress all of that information down into a dense set of numbers. Its entire purpose is just to understand. Now, the output from that encoder is called the context vector. You might also hear it called the hidden state. This is the machine's version of that core thought. It's a single vector of numbers that represents the meaning of the entire input. And that brings us to the decoder. This is a second, separate neural network, and it only takes one thing as its input, that context vector we just made. So just like our translator who now has the core idea ready, the decoder's job is simply to generate the new output based on that summary of meaning. Okay, so we have our two main players, the encoder and the decoder. Let's trace the path the data takes and see how they work together in this really clean, logical flow. The real beauty of this whole thing is its two-stage process. First, the input sequence gets encoded into that single context vector. Then, and only then, does that vector get handed off to the decoder to start generating the output. That vector is the only bridge between the two halves. And this deliberate separation, that's the key that lets the model handle inputs and outputs of totally different lengths. Now, there is a catch with this simple design. Trying to cram the meaning of a really long paragraph into one single fixed-sized vector is, well, it's tough. In early models, information from the beginning of the input could get lost or forgotten by the time the encoder finished. This exact problem, this information bottleneck, is what directly led to the invention of more advanced techniques, like the attention mechanism. So that's the theory. But where does this architecture actually show up? Well, it turns out its components are foundational to many of the AI systems you probably already know. What's really cool is that you can use these pieces separately. Encoder-only models, like BERT, are absolute masters at understanding text, which makes them perfect for things like sentiment analysis. Decoder-only models, like GPT, are all about generating new text. And then the full encoder-decoder models like T5 are the go-to for any task that needs to transform one sequence into another, like translation or summarization. And the applications are just everywhere. Machine translation and text summarization are the obvious ones, but it's also used in question answering and even for things like image captioning, where an image model acts as the encoder to understand a picture and a language model acts as the decoder to describe it in words. It really is a fundamental pattern in modern AI. All right, let's bring it all home. We've gone from the intuition of a human translator all the way to the building blocks of some of today's most powerful models. So, in one sentence, the encoder-decoder architecture works by first completely understanding the meaning of an input and then generating a totally new output from that core understanding.
And if there's one thing to remember, it's this. The real magic is this separation. By splitting the problem into two distinct jobs, an understanding job and a generating job, we unlock the machine's ability to fluently handle inputs and outputs of any length.